All right, so this is the last session of the day. We're going to move away from the non-reversible processes and look at a couple of different things. So first of all, it's Tony Maggs from ESPCI in Paris talking about multi-scale algorithms for simple fluids.
Okay, so as you've heard, I'm a physicist with a background in soft matter, working in Paris. I'm going to talk to you today about two different approaches to a multi-scale approach for simulating fluids, and it's based on a couple of papers, one a few years back and one more recently. And the idea is that I want to introduce more sophisticated, more complicated Monte Carlo moves and more and slightly different ways of doing molecular dynamics in order to study simple, dense fluids. For those of you who are not physicists or chemists, simple dense fluids are typically things that you consider as particles which just have a position associated with them. There's some potential energy between two atoms such that at very short separations there's a repulsive interaction. At larger separations there's an attractive interaction. The most standard model is called the Lennard-Jones model. So you might hear this word coming up, but it means just that. It's just that the energy is a function of the distance between two atoms. And I'm doing, I interact with a lot of people doing soft matter work. We're not interested in critical points and really exotic mathematical curiosities in the phase diagram of these fluids. We're typically away from critical points. And what I was thinking about was new algorithms that would render simulations more efficient for our chemical physics friends. So what do our chemical physics friends like to do? For instance, if I talk to biologists or if I talk to people doing simulations of simple fluids, typically you will have molecules, for instance, water molecules or argon molecules, which are then put into a box in some very simplified model, and very, very often simulations involved 100,000 or a million particles, because particularly in the biomolecular field, you're interested in, for instance, proteins, and proteins have a small, tight, interesting part at the center of the simulation. And then there's some gigantic part involving essentially water. If you don't put the water in, you get a completely wrong result. But the water is essentially a boring spectator background molecule that eats up all your computer budget. And so you're looking at some so this is maybe different to what the Bayesian people are interested in that you have, in these problems, you have some smaller physical system that you're really, really interested in, but it's embedded into some much larger physical system that you have to get right, but you're not actually particularly interested in examining the detailed properties of this larger system. But you do have to get it right to get the central, for instance, protein right or the central DNA right. So the background fluid is essentially homogeneous, dense, and non-critical. So I'm not going to be looking at phase transitions in the system. And the simulation of such a system is just slow for several reasons. There are firstly many, many particles that have to be moved in the simulation. As I said, 100,000, a million particles are not unusual in this field. The problem is that if you're using a local dynamical situation, local dynamical description, if you're doing Monte Carlo or if you're doing molecular dynamics, then you have typically conservation laws. Mass moves locally, momentum moves locally, and since things are moving locally, fluxes lead to local conservation laws. And what I'm going to be trying to do today is breaking these conservation laws by introducing global motion of particles in such a way that you break some of these conservation laws. If you do this, you're messing up the dynamics in a monstrous manner. You're not being faithful to the microscopic dynamics of what chemists are sometimes interested in. But the advantage is that you're sampling more quickly the thermodynamic properties of the system. So this is a sort of simulation which is only interesting if you're interested in purely thermodynamic properties. If you're interested in dynamical properties, the way one molecule is moving exactly in relation to another in the real physical system, the sort of algorithm that I'll be talking about today is of no use. However, Robin Ball has also got into this game of global updates in Monte Carlo, and Robin Ball has actually shown that some of these collective modes that I'll be talking about in a few minutes are actually linked to dynamics in soft matter systems, which are linked to something which is called the Oseen tensor, which is essentially a long-range hydrodynamic effect, and that in some ways these non-local cluster algorithms are linked to a realization of hydrodynamic interactions via an Oseen tensor, but I won't talk much more about that. So what do I mean about, so what happens in Monte Carlo dynamics? You take Monte Carlo dynamics, you have particles moving locally, or you have some Langevin equation, and you have a conservation law for the local density, that the density can only change by particles moving locally within the system, and there's a current which is given from a gradient of the local density. This is something we heard about this morning as well, as a typical local constitutive equation in a hydrodynamic limit. You put these two together, and it gives you slow modes, that the relaxation rate of a mode of wave vector q is linked to an inverse wavelength in the system. Omega goes to q squared, which means that in Monte Carlo, in Langevin, the number of iterations that you have to perform in your algorithm diverges quadratically with the system size if you want to sample all the modes in the system correctly. And so I did a simulation. You can even see the results on the board. This blue set of dots is a large system where I do Monte Carlo simulation of a dense fluid, and this line here on a log-log scale is the q wave vector relaxation rate, and I see that these blue dots are compatible with a relaxation in q squared. So this is this very slow hydrodynamic relaxation coming from Monte Carlo, and if you go away to your chemical physics colleagues, and they say, well, yes, of course, Monte Carlo is not very good at all. You should do molecular dynamics, and the molecular dynamics is the green, and you see that the green points have also roughly on a straight line on this curve, but the slope is smaller, and in fact the slope is 1, and so that the autocorrelation of the modes using molecular dynamics is just faster in molecular dynamics than in Monte Carlo, and so that at large length scales, molecular dynamics is much more efficient at relaxing, for instance, density fluctuations. At small dynamics, at small scales, it's less efficient. So what I'm going to tell you about today is how to get this red curve such that on shorter length scales it looks like Monte Carlo, but then I introduce essentially a plateau, and I can relax all long wavelength modes at the same rate in this fluid system. So it's at long wavelengths, it's better than Monte Carlo, and it's also better than molecular dynamics. There are many different papers that have been looking at new ways of accelerating Monte Carlo and molecular dynamics. I just give a few of the names of things that have been used in the past, both in fluids and in lattice models. In the physics community, one considers those which are successful as those which work at critical points. Those that don't work at critical points are considered as failures. But as I said already today, we're aiming to be a failure today. We're aiming to look at things that work away from critical points rather than finding algorithms which are particularly good at these exceptional points. And so firstly, let me say how our algorithm works. We introduce a multi-scale, or the term that Robin Ball likes to use is wavelet Monte Carlo. And the idea is firstly that we're going to work with blocks of particles. Rather than moving individual particles in normal Monte Carlo, we're going to choose a block of size L, and I'm going to tell you about L in a minute. We're going to displace this block in some collective manner, and we're going to have to apply some modified detailed balance relation to the block, which contains some extra points compared with the normal detailed balance criterion. And the main tactical problems that come in implementing this thing is we have to maintain reversibility. The algorithms I'll be talking about this afternoon are not the sort of algorithm we heard about this morning where we deliberately break detailed balance. And then the other thing we have to talk about is how to block and how to choose the size of the block in the algorithm. And so this is the schematic of what we do. Is we have a big 2- or 3-dimensional block of fluid where we have all these particles, and we're going to move all the particles within some circular region, and no motion occurs outside this circular block. And we want to couple to all length scales, so then we would stochastically sample different blocks of fluid using different centers to this region and different values of the radius L. So the actual algorithm is that we choose a center, C, and we use a random direction, and we move the particles, the displacement of the particle is some function, and it's going to be a function of the distance from the center of this block scaled to L. So we're going to have some master curve which describes motion on a scale 1, and we just scale it if we're looking on the scale L. And this is essentially some map, and we're going to move all the particles in this block simultaneously. And this is so this is some nonlinear map on configuration space. And the normal way of doing Monte Carlo is we do detailed balance, and we say that the flux from x to x primed on the configuration space is the same as the flux from x prime to x. But we have to be careful because of by imposing the motion using this nonlinear function g, it turns out that the step size is a function of where you are in space. And when you do that and you look a little more carefully, then what the meaning of this flux is has to be carefully treated, because essentially the flux is some distribution pi of x of size dx at x, which goes to a new distribution of pi of x primed over some new interval x primed. And we want to choose the probabilities p xx primed, p x primed x. And then we realize that by choosing step sizes which are a function of x, we've introduced essentially a Jacobian as well in the update of the positions of the particles. So if I'm doing this in one dimension, then essentially I have to introduce a Jacobian saying how the interval has been modified during the update, so that I can talk about fluxes between two small intervals being balanced. And so if you do this, this gives you a slightly modified detailed balance criterion, where you have to add in an extra Jacobian in your detailed balance criterion. So now we get to the choice of this update. What we're going to do is choose how we collectively update the particles within this circular region. The simplest thing that one might imagine would be to choose to move all the particles by the same amount within this region. This gives some fiddly, awkward things that you don't like. For instance, you do this in one dimension, then the map of x primed as a function of x, if this is discontinuous, becomes non-invertible, and so you don't quite know what to do the detailed balance type criterion. So what we actually used is a function of g of x, which is 0, again, outside the circular region, and then there's just a simple parabolic maximum within the circular region. And so if you look at the map of x primed as a function of x, the map is actually a monotonically increasing function, And so you don't get any problems in arguing about forward and backwards balancing of fluxes. This has also the advantage in that you're not scrunching up the fluid. If you were just moving everything together, then you would be scrunching up the fluid at the edge of the box. And again, this would be leading to high energy costs and low acceptance rates. And so for several reasons, we argued that this was the simplest way of updating the positions of the particles. So now the question is how to choose L. We choose the position, the center of the box arbitrarily. So each new wavelet, each new update of the system, we just randomly choose the position in the box. But we now have to choose the length scale upon which we are updating the system. Do we update some very small region which costs very little in terms of computational effort, or do we update very, very big regions which are clearly more expensive in terms of computational input? And the idea is that we want to update every length scale according to the number of independent degrees of freedom which exist at that length scale. And this is an idea in physics which is called a density of states. As a physicist, you will have studied the idea that in Fourier space, if you look at modes of vibration in a fluid or in a solid, that there's a density of states which varies as q to the d minus 1, where d is the dimension of the space for which you've chosen your fluid. But now we're working in real space. We're doing a Monte Carlo where we're choosing an object in real space. So it's natural to use this length L, which is 1 over q in this expression, and you translate this density of states in Fourier space to a density of states in real space. And this says is that you should choose the size of the circular region with a power law distribution, and the power law is 1 over L to the d plus 1, where d is the dimension of the space you're working in. If you choose that, essentially you're sampling every mode with an equal probability. And you can see that when L is small, when you're at the atomic scale, you sample relatively often. So actually you're sampling almost always at the smallest scale, but just occasionally you sample with much, much larger length scales with a probability that is decreasing with the size of the system. Now, how much effort do you actually have to take to do this algorithm? Well, you have to take this distribution of probability of choosing L, and then the work involved at the length L is just L to the d. So you multiply this by L to the d and you integrate, and you see that you get the integral of 1 over L. And so this is a log. And so the actual average effort that you need to do to simulate the system is essentially logarithmic in the system size. So the numerical effort in this algorithm only increases very, very slowly with the system size, logarithmically. And yet you're sampling every mode with equal probability, and you essentially equilibrate every mode in order 1 Monte Carlo tries. And so you've produced a sampler for this fluid with what's in the physics community, there's a dynamic exponent that the inefficiency of the system only decreases logarithmically with the system size, and so you say you've got a dynamical exponent of 0. And this is essentially what I showed you in this curve. At small length scales, this sampler doesn't bite very well onto local motion of the molecules. You actually have to be on this, and it's slightly inefficient because there's some extra algebra compared with the normal Monte Carlo move. And so at smaller length scales, it behaves like a normal Monte Carlo. But then once you start getting to larger length scales, you get all modes relaxing essentially at the same rate in the sample. And so you've produced a fluid sampler which is considerably more efficient than the standard fluid samplers from either local Monte Carlo or molecular dynamics. For it to work, you've had to inject a fair amount of knowledge about the system, that you're studying a very homogeneous system, and you know enough about the mode structure in the system to have guessed the correct distribution. So the homogeneity essentially comes about because you can use identical update rules on this scale invariant way of sampling the wavelet size. Okay, so that's the Monte Carlo part of the talk. I'm going to go on to another algorithm, which is a molecular dynamics version. Molecular dynamics version where the philosophy is similar, but we're interested in sampling in an efficient way a large, perhaps fairly homogeneous system. But again, looking towards the work of our biosimulation friends and colleagues, where they're, for instance, looking at the simulation of a protein. And the simulation of this protein is clearly very, very stupid to spend all your time moving the water molecules around the protein rather than updating the specific centers in the protein that you're specifically interested in. You would like to maybe get rid of the water or at least freeze it. And indeed, there's a large community of people at the moment in the molecular dynamics community trying to do multi-scale approaches to molecular dynamics where you follow in a very, very detailed manner what's going on in the very central region. And then at large scales, you couple into continuum elasticity, or you couple into the Navier-Stokes equations, or other continuum theories of what's going on. And then you have a very delicate problem of building good boundary conditions between your microscopically described set of particles and your macroscopically described continuum theory. Because if you've got the elastic constant, which is wrong compared with the interior, then you're going to mess up slightly the thermodynamic properties of what's going on on the inside. And so for this part, I'm going to show you how to cook up a molecular dynamics scheme where rather than sampling all the particles all the time, you freeze large parts of your system. You freeze above all parts of the system which are a long way away from your interesting center, but you still allow the system to evolve on all length scales. And so in principle, you're sampling all the thermodynamics on all length scales. And there's another point which is fairly important as well, that the chemists really like working with molecular dynamics rather than with Monte Carlo, because they're very used to this, because they've got different codes that work best in molecular dynamics, and because they're so used to, I think, interpreting data coming from molecular dynamics codes that it's sometimes difficult to persuade them to use a different approach. Manon must have heard a lot about from Werner of why people use molecular dynamics rather than Monte Carlo. You know? Werner is always saying that molecular dynamics is dead and Monte Carlo is the future. But except that the people who run the codes don't believe Werner always. So conformations of a protein. So we're doing this protein with water all around, and we still need very, very large systems, because if we don't use a very big system, there are all sorts of systematic effects, systematic errors coming in the thermodynamic properties. And as I said, there are attempts to use microscale modeling where you transition to elasticity or Navier-Stokes at large length scales. And so what I'm going to do is build a perfect thermodynamic boundary so that the whole system is equilibrated, yet you almost always do molecular dynamics only on a central region. And so the game here is we're looking at a Hamiltonian system, and the Hamiltonian system has a density on phase space which is given by exponential of minus beta h. And I'm going to work by simulating only a fraction of the whole system, so only some subset of particles described by Hamiltonian HI. And this, excuse me, I'm losing my voice today. So this Hamiltonian here contains all the interactions, all the potential energy interactions between all the particles in the system. So I've got particles which are moving, particles which don't move. The HI contains all those interactions, but it only contains the momentum part for the mobile particles. So I'm freezing most of the particles, having some particles left over, and describing them by this partial Hamiltonian HI. Then I look at the Poisson bracket between the density and this partial Hamiltonian, and I actually do a little bit of algebra, and I can check that this indeed conserves the original distribution. So if I have an equilibrated system, I freeze most of my system, but I let a subset of particles continue to work and move, then I continue sampling the same equilibrium distribution. That's the main result that I'll be using. And so now we're almost there. We can conceive of taking a central region, freezing it, taking a central region, letting that move and advance, and taking all the rest of the outside world and freezing it. The only problem is that we need a way of choosing inside and outside, which is again time reversible. And if one is not careful, there's a problem that, when particles get to the boundary, you don't know what to do with them. If they cross the boundary, are they inside or outside? How does one have a consistent role of treating this, the dynamics at the boundary, which does not break the time reversibility and the Hamiltonian nature of the dynamics? So this one is badly, you don't see it very well. So I've got a system of a set of particles, and I have a circle here, and outside of this circle, everything is frozen. On the inside of the circle, things are mobile, and they're evolving with this reduced Hamiltonian, which conserves the global measure. Now I need a rule for what happens for a particle which is moving on the inside and gets to the boundary. When it gets to the boundary, by fiat, I will say that it has a specular reflection. So this circular boundary will act as a bouncing wall for any particle that comes into it. Okay, so now I have a map where at least what's on the inside and what's on the outside is well defined. I have no particles which ever cross the boundary, because by fiat I make them reflect. And this reflection is again something which is time reversible, and so it doesn't break the detailed balance on the dynamics. Now the other thing I need to do is actually to change the radius of this circle, so that I have, most of the time the circle is small, but occasionally the circle can be very big, so that the whole system is in motion. And what I do is now choose essentially the radius of the circle from a random distribution again, Poisson distributed in time, and I insert the change of radius of the circle stochastically into the leapfrog algorithm. And what I have to do is be somewhat careful when I insert at some point in the leapfrog algorithm how I treat the events before and after the insertion. But if I'm careful, I can build an insertion of this barrier which is time reversible. And so I have now a time reversible map on phase space which conserves the original distribution function, rho. And so again, this whole system converges to a globally correct equilibrium measure, but by choosing the distribution law, again perhaps by a power law for this radius, I can concentrate all the numerical effort to the very central region, while having the rest of the thing on the outside slowly evolving and always compatible with the exact equilibrium measure that I'm interested in. And I don't have this problem of approximate boundary conditions and approximately crossing over to some continuum limit. I've imposed the exact correct outside system. So I've showed you two tricks that are valid for homogeneous fluid systems, which essentially get rid of hydrodynamic slowing down, though you have to understand the flow modes. This works by generalizing Metropolis with a Jacobian. And there was also a way of concentrating the effort in molecular dynamics around some more interesting physical degree of freedom. One can clearly combine the two as well and use molecular dynamics on the central region and resample using this optimal Monte Carlo on large length scales. And so there was two papers. And then actually there's some interesting recent work by Robin Ball and a collaborator where he points out the analogies to some of these wavelet Monte Carlo methods to Oseen dynamics. And he has a very, very nice, fast Oseen solver for polymer systems. It's a way of looking at the dynamics of polymer systems, including hydrodynamic interactions. And so he's done that very recently. Okay, so I'll stop there.
Any questions?
Yes.
Hello. So you mentioned that this isn't at all appropriate near the critical point.
Yeah.
But you also say that the correlation time is sort of independent of the length scale.
Yes.
Aren't those two? I mean, why?
Well, yeah, I would say that there's a counterexample known in the literature. For instance, when people were looking at the XY model 25 years ago, they tried to use essentially multi-grid methods on the XY model, which give, again, a z equals 0. If you're doing a solver and you're solving a set of linear equations, multi-grid gives you essentially, in physics language, z equals 0. But you use a multi-grid Monte Carlo on a spin system, and it doesn't give you any real speed up on the critical system.
And what about the glassy systems?
I've not done glassy systems, but my guess it's the same. That these algorithms are essentially sampling Gaussian fluctuations, and I would, the slow things in glassy systems are, exchanges of particles and cage rattling and rearrangements, and this method would not, I think, be particularly efficient to coupling to those motions. What's nasty in glassiness is cages and rattling and things. I see people nodding. Does anyone shake their head as well? Or I would guess that it would not be useful at all.
What's your oh,
There you go.
no, you go.
Well, so you mentioned whether MD is dead or not. So I think there might be two reasons. One is that on parallel computers, it's extremely efficient.
Yes.
So who cares if it takes a lot of effort? You just buy a bigger computer.
Yes.
And the second is maybe electrostatics. So
Yeah, okay.
Is great with
Yeah,
MD.
yeah. So that's one of my other interests is electrostatics, and the question is, can one look at these algorithms with long-ranged interactions like electrostatics? Maybe there's some hope because since Robin Ball managed to get Oseen to work, maybe one can get electrostatics to work as well.
But as it is at the moment, it doesn't.
I've got other algorithms for electrostatics. I think I can combine my algorithm for electrostatics with this, but I've not done it, so I won't say more on that. Yes.
Are you also interested in measuring correlation and autocorrelation, or is that not a quantity of interest?
What do you mean by correlation, autocorrelation?
So basically, how the system correlates it between two different times. That's typically something that you see a lot in chemical engineering, and Monte Carlo is really bad at that because you're ruining the dynamics?
So clearly, above all, the first part of the talk is you want to ruin the dynamics to go faster because the real dynamics are too slow. The second part is I try to have a central region where I conserve molecular dynamics and I mess up things royally on the outside in such a way that I do less work.
But for the central bit that you care about,
Yes.
how faithfully would it capture relaxation dynamics?
So I did some tests with some simple polymers, and it doesn't change. So it was built in such a way that essentially you don't change the dynamics on the inside. So this was the point of this second part, is that if you're interested in keeping the dynamics in the middle, because you're interested in how some protein is working, then this second half might be interesting. There was another remark maybe I could make about the molecular dynamics, because I had a talk with Manon as well after her thesis, and there are people that have coded the sort of algorithms of Werner for polymer systems, and when they did it, they almost got it as fast as lamps for polymers. Okay, so somehow, even when you push very, very hard these clever Monte Carlo algorithms and you apply it to polymer systems, then you get as fast as molecular dynamics. And so still, this is still not a magic method. There are still many, many systems where getting lamps and running it is as fast as rewriting the algorithms from scratch and using these non-detailed balance Monte Carlo schemes. Maybe you probably know much more about this than I do, because you have contacts with the authors. But
yeah, I've worked with them actually. But also, one of the big things in this paper is, can we trust the dynamics in the event chain?
Yeah.
Monte Carlo. So, like, I can speak for Werner. Werner
Yeah.
is very cautious about that, and they made all these plots about reputation of the
Yeah.
players and stuff, and
Yeah.
then they find it back with the Monte Carlo.
I would say on the polymer system as well, it would be fantastically interesting if you could have an algorithm which does not conserve the dynamics but would equilibrates quickly, because there's a big problem of pre-equilibrating your samples in polymers. You want to share a sample. And what you want to do is start with an equilibrated system, and you don't want to waste all your CPU time equilibrating your system before sharing it. So if you could, even for the pre-equilibration step, having non-realistic dynamics is fantastically useful. And indeed, people use chain breaking and all sorts of extra rules where you break up, you change the chemistry. And that's actually how you prepare the samples. You don't use the molecular dynamics to prepare your samples. You have a billion cheats to prepare your sample before starting the shear. So, if you could have a non-cheating, nice way of doing it, even if you mess up the dynamics, it would be great for sample preparation. Mike?
A related point. I mean, you talked about trying to avoid conservation laws, and in this area you're just talking about now, conservation of momentum can actually speed you up.
For molecular dynamics, yes.
Because in molecular dynamics, what it does, hydrodynamics, produces highly sophisticated correlations in your motion.
Yep, so this is going from here to there. This is Monte Carlo, this is molecular dynamics. And the molecular dynamics is faster than Monte Carlo on large length scales, because you have acoustic propagation, you have sound waves.
So but you presented at the beginning, you were speaking as though the conservation laws are always an obstacle. But sometimes they are and sometimes they aren't.
Sometimes they are, well, there's still I got my final thing to be asymptotically faster than MD. So in that sense, but it's true, sometimes, here you have mass conservation, here you have mass conservation and momentum conservation, and it's faster.
Okay, well, thank you very much, Tony.